Okay, we've got one more topic in linear algebra to cover right now before we can get on to second order differential linear differential equations. And that is the topic of linear transformations. Let me explain what they are. In basically all of mathematics, whenever you have some sort of space, right now we are studying vector spaces. And remember what a vector space is. It's something that satisfies these 10 properties. And then when you have a vector space, you can have a subset of it, which is also a vector space with the same operations. That's called a subspace. And let's see, what else have we already learned? Given a vector space, you want to be able to generate that whole space from as few vectors as possible. When I say generate, I mean you just take these few vectors and by multiplying them by constants, which is the one thing you can do, and then by adding them together, which is the other thing you do, you get the entire space. So, again, just by way of reviewing, if you think of R2, the plane, as being the space, then a very simple basis for R2 is just the vector 1, 0, which sometimes is called I, it looks like that, and then the vector 0, 1, which looks like that. So there you have those two vectors, and given those two vectors, you can generate any other vector in the space. There's a vector right there, and you can get there by doing what? By going multiplying this vector by the appropriate constant, and then adding it to that one by the appropriate constant, and moving the point if you have to, and there you go, and there you get it. So this is called a basis, right? They're linearly independent. You can't get this one from this one, you can't get this one from this one. You need them both, but once you have them both, you can generate everything in the whole space. Okay, so that's the idea of a basis. This has dimension 2, since you need two vectors to do it. And by the way, those are convenient vectors, but they're not the only vectors that'll work. Okay, as long as you have any two linearly independent vectors, let's take this one and this one, for example, okay? That would form a basis. Why is that? If you take any vector like right here, for example, how could I get there? Oh man, it's kind of hard to see it maybe, but let's see. If I take this one and multiply it to go out this far, and then this one kind of looks like this. It has a slope kind of like this. Like that, right? This slope is the same as that. So you take this vector and multiply it by the appropriate constant to get here. And then you take this vector, and you notice you're going to have to multiply it by a negative number in order to get there. And you'll be able to get there, okay? So these two vectors, form a basis. You can get anywhere you want to by taking those two. Okay? So anyway, that's just a bit of review. Then, my point is this. Now, once you have a vector space, and you can play with vector spaces, the next thing that you always want to do in mathematics is you want to be able to jump from one to another. Whether it's vector spaces or whether it's a function just going from the x-coordinate to the y-coordinate, or I should say the x-axis to the y-axis, where f of x is equal to x squared plus 1. And then you stick in values along the x-axis and you get out values along the y-axis. There you would do it. So wherever you are in mathematics, you always want to be able to go from one to another one. That's what makes things fun, is when you can travel. And so that's what we're going to do right here. So if you have a vector space, and I'm going to use the same notation as the book, if this one is V, and we'll call this vector space W. Notice now that W is not necessarily, it's not a subspace of V. I'm just using V and W as my two vector spaces. Then a function travels from one to the other. Now, you know what a function is already. A function is just anything that you stick in a value and you get a value out. So by sticking in something here and doing something to it and getting out something there, that would be a function. But we want our function to have more, be a little more restricted than that. If you think about it, the two things that are important about vector spaces is that you can add vectors together and that you can multiply them by constants, right? Those are the two things you can do. And so a linear transformation is going to be a function that goes from one vector space to the other, which preserves these two operations. What do I mean by preserves? Here's what I mean. I mean that if you take, let's let t be the linear transformation. T is a function from v to w. It's a function from v to w, and it satisfies two properties. The first property is that if I take any two things in here, x and y, and I add them together, and by adding them together, of course, I know this is a vector space, so x plus y is also going to be in here. Maybe this is x plus y right there. Okay? So here's x plus y. Here's what the linear transformation has to satisfy. T of x plus y has to be equal to t of x plus t of y. Okay? So let's think about what that means. It means that if x gets sent right there, here's t of x, and if y gets sent right there, here's t of y, and of course this is a vector space, so I can add t of x and t of y together, and if I add them together, maybe I'm right there, t of x plus t of y. If I add these two things together, I'm going to end up right there. Turns out that if I were to add them together first, see this? If I were to add them together over here in v, get x plus y, and then take t of that, I'm going to end up at the very same spot. Okay? So in other words, it doesn't matter whether I first add them together and then send them over, or whether I first send them over and then add them together, I'll end up at the very same spot. You can kind of think of it as like ordering something from Amazon.com, where it doesn't matter whether they first put it together and then send it to you, or whether they first send it to you in two pieces and then you put them together. Either way, by the time you're done, you end up with the same thing. You can put it together first and then send it, or you can first send them and then put them together, and you're going to end up at the same spot. So that's one thing that has to be true in order to be a linear transformation. The other thing that has to be true, can you almost guess what it is? Linear transformation, vector spaces also have, of course, this property. So that also has to be preserved under the linear transformation. In other words, I can first take my x and multiply it by a and get something there. And then once I have ax, here's t of ax right there. Or, what can I do? I can first take my x and take t of x right there. And once I have t of x, then I multiply this thing by a. And again, it doesn't matter what order you do it in. I can first multiply it by the constant, then take t of it, or I can first take t of it, which means to first pull it over and then multiply it by the constant. Either way, I'll end up at the same spot. Okay? So that's what a linear transformation is. We say it preserves basically the operations of the vector space. Okay? And by the way, this vector space might be very different from this one. This one, if I'm adding them together, maybe I use a plus sign here. This one might be a different kind of plus. So I'm using plus for both of them. But to be a little more exact, I should maybe indicate that this is a different kind of addition. Maybe this is a different kind of multiplication than over here. So it could be a very different kind of vector space. As long as these are both vector spaces, you're fine. Okay? So, of course, if it's a vector space, each one of these things has an identity to it. Let me just start over again here, make it cleaner. So here's your V, here's your W, and so we have an identity here. Now that we have two vector spaces, we're going to have to identify which identity we're talking about. So let's call this theta, which stands for the identity sub v, and let's stand for this. Let's let this one be theta, which stands for the identity sub w. Okay, so they each have an identity. And you might think that it would be reasonable that if you have a linear transformation that goes from one to another, that it would take one identity to the other. And in fact, that is true. It's nothing that we state has to be true, but it turns out it is true. So let's write it. Let's prove it as a theorem. Okay? So instead of writing this all out, I'm just going to say T of theta sub v is equal to theta sub w. It takes one to the other. Okay? Let's prove it. Okay? There's just an example of another proof. Okay? So let's prove it. Here's how we prove it. Proof. First of all, T of theta sub v is equal to T of theta sub v plus theta sub v. Agreed? Because this is the identity, so I can add it to anything, and I haven't changed it. Now I can make use of this property of linear transformations and say that's going to be T of theta sub v plus T of theta sub v. I know that. Okay? And I can also say that, let's see, what else do I want to say here? I want to say that, T, so I'm just going to write this. I'm going to say also T of theta sub v is equal to T of theta sub v plus theta sub w. Agreed? T of theta sub v is over here. It's over here someplace. You're over here in w. And if I take anything in w and I add it to the identity, I just get that same thing back again. So this is equal to this. Okay, I'm over here in w. If I take anything in w and add the identity to it of w, I get the same thing back again. So now I see that this is equal to this, and this is equal to this. So I can say, so T of theta sub v plus T of theta sub v is equal to T of theta sub v plus theta sub w. And now I can use one of the properties that we had back when we first learned about vector spaces, that if you have this, then you can basically cross those off, take the additive inverse of each of them, get rid of them, and so we can say, so T of theta sub v is equal to theta sub w. So there's our proof. There's our proof that an identity goes to an identity. Okay? And that's as much as we're going to prove with linear transformations. I now want to give you a bunch of examples of them. That's going to be the more important thing to do. So let's look at several examples, and there's a bunch of them in the book. I want to take ones that are just a little bit different from in the book. Here's the ones I want to do. Let's let T go from all differentiable functions. This means that you have functions that you can differentiate as many times as you want. Okay, if you have x cubed, I can differentiate it and get 3x squared, then 6x, then 6, then 0, then 0, then 0, then 0. You can differentiate it as many times as you want. On the other hand, if you take x to the 7/3 and take its derivative, you're going to get 7/3 times x to the 4/3. Take its derivative, you're going to get 28/9 times x to the 1/3. And you take its derivative, and you're going to get 28/27 times x to the -2/3. And notice that this does not accept 0. So these functions all have a domain including 0. This one does not. So this is a function where when you take the first, second, third derivative, it's no longer a differentiable function. It no longer is differentiable on the entire domain. Okay? So not all functions you can take the derivative an infinite number of times, but we're going to assume that we're looking at the ones where you can. Okay? So there's our linear transformation. Both of these sets are going to be the same. So both of these vector spaces are going to be the same. They're both going to be this. And here's what I'm going to do in order to get from one to another. I'm going to take some function in here, and I'm going to take its derivative. Okay? So that's how we get from here to here. So let me again redraw this picture. So here is C like this. Here's C like this. And here's our linear transformation T. And what does T do? T takes something in here and takes its derivative to get over there. Okay? So T of x cubed would be 3x squared, and so on. That's what it does in order to get from here to here. Okay? Now, so first thing let's do, let's prove that this in fact is a linear transformation. Okay? So let's prove, let's say T is a linear transformation. Let's prove it. Okay, how do we prove it? Well, let's see here. If I take T of f plus g, T of f plus g is equal to, by definition, what does T do? It's the derivative of f plus g. Right? That's what T does. It takes the derivative of any function. But now, here's something that you learned in calculus. You learned in calculus that the derivative of the sum of two functions is the derivative of the first plus the derivative of the second. That's something you learned in calculus, and so we're not going to do that again here, but that's true. And once you've written it like that, you just notice that that's T of f plus T of g. So there we have just shown that T satisfies the first property needed to be a linear transformation. What's the second one? T of some constant. I guess I'm using A as my constant. I'll use alpha. I'll use alpha just to make it really clear it's a constant rather than a function. Alpha f. So by definition, what's T of anything? It's the derivative of that thing. And what did you learn in calculus again? You learned that if you have a constant times a function, its derivative is just the constant times the derivative of the function. That's something I'm teaching a calculus course right now. I just taught that to them last week. Okay? And once you have that, notice that that's just alpha times T of f. And that's why in almost every calculus book that you'll ever pick up, these two things are always grouped together in a calculus book. They don't tell you why, but they always group them together because the author has in mind that differentiation is a linear transformation. That's why I think I told you, that's why it is the case that linear algebra is really kind of an underpinning of a lot of mathematics, almost all, just a lot of mathematics. Not all of it, but a lot of it. And so here's just one example where it is the underpinning of differentiation. Differentiation is a linear transformation. Okay, so that's a linear transformation. That's just one I want to show you. Here's another one. Let's take this one. Let's take T from R3 to R2. Given by T, anything in R3 is something of the form x, y, z. Agreed? Here's your x-axis. Here's your y-axis. Here's your z-axis. And so you go along the x-axis, then you go along the y, and then you go along the z, and you end up someplace right there. So we're going to take the point x, y, z. There's some vector in R3. And let me make sure that you're still with me here. Whoops. Okay, very good, you are. Okay, and here's what it's going to do. It's going to send this point to just the point x, y, 0. Okay, so physically, or I should say graphically, it takes this point and it just sends it straight down to the point xy on the xy plane. So it's sometimes called a projection because you can think of there being the sun or a projector up above here and the shadow of this point on the xy plane. If you think of the xy plane as being the floor, it just takes the shadow of this and it just goes straight down to the point xy 0. xy 0. Okay, so that's also a linear transformation. Heck, I'm gonna leave. Well, let's do it. So t of x1, y1, z1 plus x2, y2, z2. There's 2 points right there. T of that is, well, what is that? I guess we first need to add them together. This is t of, if you add these two together, you're going to get x1 plus x2, y1 plus y2, z1 plus z2. If you add those 2 points together. Now, what does t do to that? It just keeps the first 2 like that and puts a 0 in the last place. And so that's what t does. And notice that now I can write that as just the vector x1, y1, 0 plus x2, y2, 0. And notice that this is just t of x1, y1, z1 plus t of x2, y2, z2. So sure enough, t of the sum is equal to the sum of the t's. Okay? I won't go through with the constant. It's very similar. Okay? So that's also a linear transformation. Okay, very good. Now, this is where I wish we had more space, but I think maybe I can do it here. Couple key things which are important here. If you have a linear transformation, the kernel of t is all the things in, let's call this x now, v now again, and this w. The kernel of t is all the x's in v such that t of x is equal to the identity vector over in w. Okay? So the kernel of a linear transformation is all the stuff over here. Maybe it's a whole group of stuff over here, all which gets sent to the identity over there. So it could be a whole lot of stuff over here, all gets sent to the identity over here. That's called the kernel. So with these 2 examples, let's find the kernel of each one. What's the kernel? Let's first take the kernel of this one. What's the kernel of this one? Notice that in R2, the identity is just the vector 0, 0, right? And in the R2 plane, the vector is just the 0 vector, the origin. So what are all the things in R3 which all get projected down to the origin? Do you agree? It's basically all the things right along the z-axis. All the stuff along the z-axis is going to get projected to the origin. So here we could say that the kernel of this t is everything of the form 0, 0, z. Okay? It's everything of the form 0, 0, z. Everything along the z-axis, all of that is going to get taken to the origin. Okay, so that's the kernel of that linear transformation. What's the kernel of this linear transformation? Well, let's see. It's all the things that get sent to the zero vector. The zero vector here is just your function, which is identically zero. Just the function which is identically zero. That's the thing that you can add to anything and just get that function back. So what are all the things over here? Let's put this back and call this all the differentiable functions again. Here's all your differentiable functions. What are all the things that get sent to the zero function? To f, which is identically zero. What are all the things over here which get sent exactly to the identity thing, vector? And I hope you agree that it's just all the constants. It's just all the constants. Let me just say all constant functions. Right? F of x equals 5, f of x equals 13, f of x equals e squared plus 7. Okay? Any constant, its derivative is 0, so that would be the kernel. That would be the kernel of this. Okay? So, very good. Let's see if there's anything else I want to. I guess I'm not gonna try to cover everything in this section. I'm just gonna cover the kind of the key things. Whenever you have the kernel, or let me explain it this way. Let's go back to R2. What were the subspaces of R2? Do you remember what they were? They're all the things that you can take two things and add them together and you're still going to be there. So all the subspaces of R2 were the lines through the origin. So there's a particular subspace. Okay, there's a particular subspace of R2. If you take any subspace of R2 and you just kind of take it and add a constant to it, you're going to, here, you just add a constant to all of those vectors. You're just going to get some other line which is parallel to the original one. And this thing right here is called a subspace. This thing right here is called an affine subspace. Okay? So the first thing to notice is that an affine subspace is not actually a subspace. Okay? So this is not a modifier to describe a certain kind of subspace. Instead, this is one word, which means this is what you get when you take a subspace and you crank it over so that it's no longer a subspace, but it's not necessarily a subspace, but because you've taken it and you've cranked it over. It's not a subspace in particular because notice it doesn't have the zero vector in it. Okay? It doesn't have the identity vector in it. But you've just taken one and just moved it over. It's called an affine subspace. So basically, an affine subspace is what you get by taking all the vectors along a subspace and you add the same constant to it, or the same, I should say, the same vector to it. And by adding the same vector, then you get this whole other set right there. And that's called an affine subspace. So an affine subspace of this, let's erase all this stuff. Oh, I know what I haven't done yet. So okay, so I explained affine subspace. Now I want to talk about prove one more thing. I guess we have a couple more proofs here. Okay. The kernel of a linear transformation is a subspace. Okay? The kernel of a linear transformation is a subspace. Let's prove it. Here's the proof. Okay? What are the two things you need to show in order to show that something is a subspace? Remember, we have to show that if you take any two things in there, it's also in there, and if you take anything times a constant, it's in there. So let's do it. So let's prove, let x1 and x2 both be in the kernel of T. Okay? Okay, so we want to show, then, here we go, then let's say must show that x1 plus x2 is in the kernel of T. I guess I'm going to write it like that as well. And also show that alpha x1 is in the kernel of T. We have to show both of those things. Okay, let's do them both. Okay, so here's how we do it. So T of x1 plus x2, well, it's a linear transformation. So that means I know I can write it as T of x1 plus T of x2. And since x1 is in the kernel, I know that x1 gets taken to the identity. And since x2 is in the kernel, I know that that gets taken to the identity. But I also know that the identity plus the identity is just the identity. And look what I've shown. I've shown that x1 plus x2 gets taken to the identity. And so I've just shown that indeed that thing is in the kernel. It gets taken to the identity. Okay? Let's do this one. T of alpha x1, I know is equal to alpha times T of x1. T of x1 gets taken to the identity. And now I know, again, from what we did back when we first started learning about 2 lessons ago, if you take the identity of any vector space and multiply it by a constant, you just get the identity again. See why that stuff was so important? And so there, I've shown that this thing right there is also in the kernel. Because what does it mean to be in the kernel? It means that T of that thing gets taken to the identity. So we've just shown that these things are both true. And so we've shown that this thing here is a subspace. Okay? So that thing right there is a subspace. So, I just want to say one more thing with regard to this chapter then. That, let's go back to these 2 examples we have. Here was R3. T of x, y, z is equal to, what was it? X, y, 0. It just got projected down to the plane, right? So the kernel is everything that gets taken to the identity. So the kernel was all this stuff, and that's a subspace. And now what did we learn that an affine subspace is? An affine subspace is what you get by taking any subspace and just translating it over. You're just taking it and adding a vector to everything there, and you get something over here. So if I take all of these vectors here, and I just add the same vector to them, I'm going to get another line right there, and I'll get an affine subspace. So there's the kernel, that's a subspace, and there's an affine subspace right there that doesn't go through the origin, but it's right there. Okay, so there's one. Let's do the same thing here. What's the kernel of this? Of this linear transformation? For this one, the kernel of T is just all the things that get sent to the zero vector, so it's all the constant functions, right? It's all the constant functions. Because they all get sent to zero. So you can kind of think of it like this. T of f takes the derivative of everything. So here's all the constant functions right there. And all of those get sent to the zero vector. Agreed? Take the derivative of all the constants and you get sent to the zero vector. So so that's your kernel. That's your kernel. But then if you take all the constant functions and just add the same vector to all of them, let's take all the constant functions and just add x squared to it. X squared plus the constant functions. Then what are you going to get here? Then you're going to get all the, when you take the derivative of all these things, you're just going to get 2x for all those things. So the derivative of all of them is 2x, but this right here is an affine subspace. This right here is an actual subspace. All the constant functions is a subspace. Okay, you can show that all the constant functions is a subspace, and if you take all the constant functions and add x squared to it, you're going to get yourself an affine subspace. So this subspace contains 0. That's the identity. This one doesn't contain 0. It contains x squared plus 0. That's not the identity, but as I say, an affine subspace is just what you get by taking a subspace and just adding a vector to everything, and then you get an affine subspace. Okay, so that's kind of, those are the key things you need. I'm basically going through several days worth of linear algebra theory and just kind of pulling out the most important stuff that you need for this particular course. And hopefully you've already had linear algebra in your background, but if not, even if you have, this is a bit of a review, which will help you with the stuff that's now coming up as we get into second order linear differential equations. Very good.